Welcome to the series Photographic Chemistry, presented by the Foundation of the American Institute for Conservation of Historic and Artistic Works. This program was made possible by grants from the National Endowment for the Humanities and the Andrew W. Mellon Foundation. Each program in this series is presented as a short video. Depending on your video viewer, you should be able to pause, return to a previous section, or skip ahead to a later section by using a scroll bar or on-screen icons. You will find an outline of the course and short quizzes to test your understanding on the course webpage.
We may now put all these concepts together, from the emulsification reaction, the single and double jet emulsification process, all the way through to how we use KSP to engineer the silver halide materials that we use in film and paper-based photography. To do so, let's go to a couple more whys so you get used to seeing these numbers and why we do what we do in photographic chemistry. Using KSP, I can illustrate another why in the photographic process. Why do we tone? The KSP for silver sulfide, as an example, is 10 to the minus 51. This is, again, over 25 factors of 10, even less soluble than the least soluble silver halide. What this says is that if you place silver sulfide in any kind of a water environment, the most you can achieve is about 1 times 10 to the minus 26 molar silver, practically insoluble. How did I get that number? Remember, it's the product, the solubility product. So the concentration of the cation, or the silver, with the concentration of the anion, in this case sulfide, the product of those is going to be equal to 10 to the minus 51. So you just take the square root of 10 to the minus 51. It's a lot of math, but what does it mean? Practically a vanishingly insignificant value of solubility. This silver sulfide is going to go nowhere anytime soon. As opposed to, why do we fix? The solubility for silver thiosulfate is orders of magnitude more soluble than the silver halide salt itself, 10 to the minus 5. So it's much more soluble. We're starting to approach the solubility of table salt at, remember, 10 to the minus 2. So this is why we fix. This is how we remove silver halide from photographic papers and films. So let's go back to our single jet experiment, how we use KSP to precipitate silver halides out into the gelatin emulsion. Remember I said that in a single jet experiment, the halide salt will be at about a 1 molar solution. If I add, and this keeps the math simple, if I add 1 molar silver nitrate to that in a single jet process, then what the KSP says is I can't have silver ion with chloride ion in a concentration any higher than 1.77 times 10 to the minus 10 molar. Cannot be any higher than that. So what this means is when I'm starting out with 1 molar and I mix the two together, the concentration is way out of equilibrium. It's way too far on the right-hand side of that equilibrium equation that we looked at a couple of slides ago. What does nature do? Nature notices this imbalance. We're way too heavy in ions. For her to readjust this, she has to precipitate or make more solid. In equilibrium, we say we're going to shift this to the left. We're going to shift this to the reactants. We're going to make more solid. And we're going to continue to make more solid, or silver chloride will continue to crash out until the solution's concentration of silver in the water is 1.6 or 1.7 times 10 to the minus 10 molar. This situation happens even faster, more complete with silver iodine. If we have a mix of chloride and iodide in the same solution, then the equilibrium is going to be much more sensitive to the iodide that's present in the solution. And so when the precipitation happens, we're going to be precipitating silver iodide out at a rate much faster than the silver chloride is going to precipitate out until the balance is reached. So we will tend to precipitate more silver iodide than chloride if everything were equal. To fine-tune this process, we change the concentration of reactants so that we know exactly the proportion of the chloride with the iodide or the chloride with the bromide with the iodine in each and every grain. The solid-state precipitation chemistry is a lot more complicated. How you control that is a lot more complicated than what I'm describing, but it makes intuitive sense that the least soluble salt, the iodide, is going to precipitate out more than the most soluble silver halide, which is the chloride. And so if I adjust the proportions, I'm going to adjust the amount of each species in an emulsion solution. This translates into different sensitivities, both to exposure intensity as well as to the wavelength of light that hits the light-sensitive material. Now that we know how silver halides are formed, we can now begin to explore the different chemical and physical properties that each of the silver halide grains possess. We've already discussed the solubility differences between, for example, silver chloride and silver iodide, and there are substantial differences in the grain solubility. But these silver halides also have substantial spectral absorption or light sensitivity differences. Another key difference between each of the silver halides is their chemical adsorption properties. And we'll go into why this is important in photographic chemistry, and then wrap up this section with a discussion of how each of the silver halides impacts what is known as the crystal habit, or the crystal morphology or crystal shape.
You have completed this unit. Depending on your video viewer, you should be able to scroll back to any point in the video as desired. The short quiz found in the course materials on the website may help you confirm your understanding of the concepts introduced here. Many thanks to the instructor, production editor, coordinator, and the Collaborative Workshops in Photograph Conservation Committee for their work to make this program possible.